In this video, we'll go back over the geometric representation of the integral as the area under the curve. What does it actually mean to compute the area using the rectangles that I mentioned in the earlier sections and the videos as well? We can use different shapes, the actually well-known shapes. So we'll actually compute the area and then we'll tie it all together with the antiderivative once again in section 6.4 in the next video. So, how we can approximate the area under the curve, literally using the rectangle. So let's say if we use 4 or 5 of them, and let's say the width of each rectangle is always going to be the same, we'll call it delta x. And in this case, it's not going to be 0, it's not going to be small necessarily, but we can easily find it. It's the length of the interval, which is b minus a, divided by number of rectangles, n. So once we find the width, then we can draw it. Let's say we're using 4 rectangles, and let's say we're using the shape f of x. So I tried to draw it. If you'll notice that each rectangle is touching the curve at the left endpoint, as I can kind of emphasize. So as you are drawing out the interval, you can find each endpoint, the x1, x2, and x3, by adding the delta x, the width. Once you find it, then you start at the a, which we'll call x0. Add delta x, you'll get x1. Keep adding delta x to get x2, then x3, and then finally you'll get the last endpoint. So typically we'll have one more endpoint than we have the number of rectangles. So if we have 4 rectangles, we'll have 5 endpoints because we're starting at the x0. So notice you can actually choose each rectangle to touch at the left endpoint. Again, it's just so that we know how the height of each rectangle is. So we can choose it to touch the function on the left, for example, as you can see in this picture. In this case, the area under the curve, you'll notice how some of the rectangles would be under the curve and some would be over the curve. So let me pause this video a little bit that I can show you what each area is going to look like. Okay, we're back in the video, so I'll show you. So here's the first rectangle, and the next one, and then the next one, and then the last one. So you'll notice it's not quite the area under the curve. You'll notice some of the white spaces. You'll notice one of the rectangles sticking out. So just keep in mind, it's just an approximation. It's not as good as the integral, because that's actually the limit as n goes to infinity. But that's how you get the idea of how to actually do it. So how to compute the actual area is one of the ways is to multiply the length times width, but since the width is always the same, we can factor it out. So we'll have delta x times, and then the height of each rectangle. Let's say if for the left sum, we'll start with f of a, the leftmost endpoint. You'll see that's the height of the first rectangle. Then f of x1, which is the height of the second rectangle. Then f of x2, the height of the third one. Then f of x3, the height of the fourth one. Here's all 4 of them. Notice how we didn't actually quite get to b, but that's okay. And now you can also do the same thing with the right endpoint. You literally, it doesn't matter which one you use because each one's approximation. Actually, if you average both of them, you'll probably get more accurate idea. But here is the right sum. It's done very similarly. As you'll notice, there's 4 rectangles and you're trying to compute the area. Once again, some of them are sticking out. But how do we compute the right sum? Again, the width is the same, so we factor out delta x. And then we're actually starting the height of the first rectangle is f of x1. So right here. And then the second one's f of x2. The third one is f of x3. And the last one is f of x4, or b. So in this case, we did not start with a, but we did reach b. And that's how we'll get the right sum. And again, it's just an approximation. And the midpoint tends to be a little bit more accurate just because the rectangles do not actually stick out as much, as you'll notice. So how do you do it? Again, it's the same interval, the same width, same endpoints that you can plot out, but then you pick a midpoint of each interval and you have the rectangle cross the function right in the middle. So here's the first one. I went outside of the lines a little bit, but here's the first one, and notice it only sticks out a little bit. Here's the second one, the third one, and the fourth one. And I'm not actually going to write out the formula because it looks a little bit confusing with the older notation. But again, you would have to find the midpoint of each one and plug it into the function, and that's how you get the y values. And here is a quick little applet that, let's see if it actually works, but I could show you. Let me quickly show you if my Java would actually work. Now I'll remember, and we'll see if it works. Okay, it may not. So let me go back. As you've noticed in your little Java, basically what I was going to show you is the little applet that you can choose the n to be different numbers like 250 and so on, so you can actually see how close to an approximation of an area it becomes. So maybe I can show this in class, but you can check it out yourself, and hopefully your Java is enabled. And anyway, how do we apply it is very simple. If we have a function or a graph, if you have a graph, you may have to read the y values of the graph. But if you have a function, here is the interval, 0 to 2, n equals 4 for rectangles. So how we find the width? It's 2 minus 0 over 4. In this case, it's 0.5. And then we set it up the left sum as the width, 0.5. Again, a lot on these homeworks, we would be asked for the left sums, but you can easily find the right sums as well. But how we find the left sum? Again, we start with f of 0, and you can keep adding the width to generate the endpoints. So the next one would be f of 0.5, and then plus 0.5 is f of 1, and then f of 1.5. And notice we do not quite reach 2. And how do we get all these y values? You can plug in these x values into the function. So 0 would give us negative 1. 0.5 times 4 is 2, minus 1 is positive 1. 1 times 4 is 4, minus 1 is 3. And then 1.5 times 4 is 6, minus 1 is 5. And altogether it's 8, I believe. 3 plus 5. And times 0.5, and it's 4. And if we calculate the right sum, it's a similar idea. Here's the width. But notice how instead of starting with f of 0, we're starting at the next one, f of 0.5 plus f of 1 plus f of 1.5 plus f of 2. And I actually draw out the endpoints just to count them out. And if you can draw the graph, try to draw the graph as well. But sometimes it's a little bit tricky, so I just draw out the endpoints. Anyway, you can do it similarly in number 3. If f of x is x squared, the interval is from negative 2 to 2, and n equals 4. Once again, now in this case, the width is 1. How did we get that? 2 minus negative 2. That's 4 divided by 4, so we get 1. And the left sum, once again, it's the width is 1 times f of, we're starting with the left endpoint, negative 2, plus we keep adding 1, so it's f of negative 1, plus f of 0 plus f of 1. Here's all 4 rectangles, so we stop right here. Once again, we plug them in into the x squared, and we get 4, 1, 0, and 1. And I think in class I actually drew this out, and you can do that as well. And to visualize it, let me actually attempt to do it in this video. It's a bit hard to draw on this tablet, but let's say if we're from negative 2 to 2, you're visualizing the x squared and the area under the curve going towards the x-axis. So if we're doing the left sum, you're starting at the leftmost endpoint and then extend out. So here is the first rectangle, pretty much, and then you're touching the curve and going back to the next one. Then you may have a 0 length rectangle, which basically looks like a line, if I can make it dark, right here. And then it's touching at the 1. So here we have 4 rectangles. So here is the first one, here's the second one, the third one was 0, and here is the fourth one. So they all basically have same width if you draw this correctly. And so notice you may have a 0 for the height of some of the rectangles. And since we're just being asked for the left sum, we'll leave it right there. Number 4, it's really the same idea, but from 1 to 5. So again, the width was 1, and you start 1, 2, 3, 4, and you stop 1 short, so you get 30. You can do this with 5 rectangles, e to the negative x. Let's say the interval from 0 to 10. Hopefully you can see why the width is 2, but we'll start with 2. And then again, we start with 0 and we keep adding 2 until we get 5 rectangles, 2, 4, 6, 8. And we have 5 of them. And once again, you may have to, so see how I wrote them out, put them in the calculator. Actually put them like this. If you have a graphing calculator, just put them like that and then times 2. And then I'm getting 2.3129. So the more exact you are, the better. And same thing, as you'll notice, you may have to look at the graph to get the y values, but it's the same kind of idea if you're given the graph instead of the function. So, and same thing in number 16. So you may have 3 rectangles and it's from 0.5 to 3.5. So it's kind of same idea. Start with 0.5 and keep adding 1. Then it's 1.5, then it's 2.5. And read it off from the graph. And going to the next point, we can use geometry to relate it to the area under the curve besides the Riemann sum. So let's relate it back to the integrals a little bit. So this is called the definite integral from 0 to 2. We'll learn how to do that in the next section. But it's basically the graph of y equals 5, this is our function, on the specified interval from 0 to 2. And if it looks like a geometric function or graph that we know, which it does, if 5 is a horizontal line and extending down to 2, notice it looks like a rectangle, if I can color it. And we know how the shape of the rectangle, the area is basically the length times width, which is basically 5 times 2, which is 10. And that's the answer to the integral. So if it's a basic shape, we can just do it via geometry without even using integral. And so sometimes it's quicker, so if you know that, you can actually use it. What if it's an integral from 1 to 2 of x times dx? In this case, we have y equals x. How did I get this graph? Well, at x equals 1, the y is 1. And at x equals 2, the y is 2. So we have this straight line. But notice if you actually extend it down, it looks like a trapezoid, but it's hard to remember area of a trapezoid, but you can subdivide it into a rectangle and a triangle. So if it's a rectangle, if you'll note, the base is 1 and the height is 1. So it's 1 times 1. Area of a triangle, you do actually need to know this. It's 1/2 times base times height. So it's 1/2. The base is 1 once again and the height is 1. So altogether is 1.5 or 3 over 2. Now let's look at a couple of applications, how we can use Riemann sums with doing the integral, or without doing the integral actually. So let's say if a marginal cost of MP3 players is given, it's 20 minus x over 200, where x is the number of MP3 players manufactured. Use the Riemann sum with n equals 5 to estimate the cost of producing first 5 MP3 players. Now please note, it doesn't actually tell us left or right. However, well, first of all, we know it's n equals 5. The interval is not given, but we can guess it's 0 to 5. You want to start with 0 because you may have fixed cost and go all the way up to 5. The width of each rectangle is 1. So let me show you how I set this up. I did start with a 0. Technically, it's a left sum. Why? Because if you remember, marginal cost approximates the cost of next item. So if you're starting with C prime of 0, it actually approximates the cost of the first item. And then you can keep going. Keep adding 1. C prime of 1 approximates the cost of the second item. C prime of 2 is the third, and so on. So all the way up to C prime of 4. So really it's a left sum. And again, we can plug in the 0 is easy. So we get 20, and then use your calculator for the rest. So I'm getting these values. And altogether we get $99.95. And that's actually the total cost of the first 5 items. So here's how we can interpret which Riemann sum to use. And here's one velocity question that is on the homework. So let's take a look at that. Let's say we have a stone that's thrown up at 30 feet per second. And we're given a velocity equation, negative 32t plus 30 feet per second. Use the Riemann sum once again with n equals 5 to estimate the integral from 0 to 4 v of t dt. What does the answer represent? So You can see the example on page 492 to help you understand it a little bit better and back in the textbook. But basically, the distance covered is equal to the total change in position, which is this integral. And we can use the Riemann sum, and because it's from 0 to 4, it's basically 4 minus 0 divided by 5, which is 0.8. So you can have a decimal with, which is fine. Change in position is approximately equal to, approximately because we're only using 5 rectangles to estimate it. And again, it looks like a left sum. 0.8 with velocity works very similarly. V of 0 actually represents the position at 0. And we can keep adding 0.8. So V of 0.8 plus V of 1.6 plus V of 2.4 plus V of 3.2. And again, you can plug it into the velocity to get all these numbers. And altogether, we calculate the approximate distance position as negative 84.8 feet. So we have been using the left sums pretty much throughout this section, but also make sure to practice the right sum, and if you can, the midpoint sum as well to get the idea. And that's it.